Good evening, friends, and warm welcome to the seventh in the series webinar by eDiscovery Tata Tiscon. I thank Tata Tiscon for giving me opportunity to connect this pan-India like-minded colleagues of mine to share my experience in structural repair and retrofit. Today's webinar will last for around 50 minutes, and you can ask me questions if you have. At the end of the webinar, we have kept 10 minutes for that, and we can address your queries at the end of the seminar. So again, thanks a lot for connecting. So today's topic of webinar is latest trend in structural repair and strengthening. We can call broadly as structural retrofitting, means whatever activity we do in terms of repair and strengthening can be classified as structural retrofitting also. As a civil engineer, we come across different situations like this in practice, and we need to offer engineering solution for this type of problems. This can be the one like we are seeing currently on this photograph, or this type of damages which are sort of earthquake damages, or this type of failures, structural failures of a structural element, in this particular case this silo, or this type of bad quality of concrete, honeycomb area, and this type of bad quality of concrete may link to this type of collapses, or critical infrastructural projects like bridges. You can come across this type of situation, and this type of situation puts us in really very tight position, and we need to offer solution in this type of problem. But we should think, like, after seeing all these photographs in previous slide, definitely few things come into our mind, that why these incidences happen. First of all, like, what is the reason? Analysis and diagnosis is a basic part of it. And what is the common in all these photographs which we seen in our previous slide? I normally get different answers for this: lack of supervision, inadequate design, or many other things. But one reason I always feel from the last 15 years, that the basic reason for this type of issues is a total neglect. Like, we don't care about this. As a civil engineer, we are not caring the way we should care, and we are absolutely negligent about that. And that really puts doubt on our profession, and we have to really face music from different agencies. So let's address this type of issues, and let's see what care we need to take. So today's learning objective, that what we are going to what I'm going to discuss, or what I'm going to share with you, is basically need of structural repair and retrofit, like why we need to retrofit the structures. Then what are the factors affecting durability of RCC structure? We, being a civil engineer, are taught lots about strength, but of late durability has become more important. Like, we are strong, but we are not going to last for long, so we don't want that type of structures. We really want durable structures. So what are the factors, and what are the factors we should take care? We'll understand the phenomenon of corrosion in RCC structure. What are the factors responsible for corrosion? Then we'll discuss different strategies for structural repair and retrofit. Then we'll also discuss what are the most advanced techniques available for structural repair and retrofit. And at the end, we will discuss few case studies. I have a tough task today, because normally I talk separately on repair and separately on strengthening, or rather I talk separately on corrosion and separately on strengthening. But today I tried to club both the subjects in a prescribed time, and I like to brush on the issues. At least you will come to know what are the issues. We can have subsequent discussion for detailed studies. So why we need to retrofit the structures? What is the need of retrofitting the structure? First, come in our mind or we come back to a situation is change in use. There are different situations, like uh, we have a residential building and we want to convert its use as a commercial structure, or we want to convert it as a school or hospital. So naturally live load will increase and you need to ensure that your structure is capable of that additional load. New equipments, many a times, especially in industrial structure, we end up putting new equipment, and your existing frame may not be capable of taking that type of load, so we have to offer solution. Then seismic retrofit. All old structure are not complied for current seismic code, and as a good safety practice we should ensure that our at least infrastructural projects or lifeline structures are upgraded for current seismic demand. So in that situation we need to do for seismic retrofitting, and blast upgrades for the structure which are very sensitive from safety and security point of view. Then comes the deterioration. As you know, deterioration is a natural process, and when you talk about deterioration, I think corrosion is a single largest factor responsible for damaging the structure. And because of corrosion, there will be loss of section, there will be cracking, there will be exposure of acidic environment, and we need to offer solution there. Then this is also very interesting area. I think almost we are getting almost 25-30% cases of faulty construction. Means nowadays quality parameters has really gone up, and your quality has been monitored at every stage and reviewed by different agencies, and we found that reinforcement is not properly placed, or many times we find missing reinforcement or incorrect reinforcement detailing at many times. Low concrete strength. Now we are in the age where we are recommending really high grade of concrete, M60, M70, and MNT, and producing that consistently is a challenge. It's not easy to produce that type of concrete quality consistently, and in the process if we fail, we come to know after 28 days. So many a time it's not possible to demolish it, so we have to offer some solution to retrofit the structure. Then structural damages. Structural damages are mainly because of impact and excessive wear, and fire. Means at least in a year we come across 3-4 different fire damage structure where concrete get damaged because of exposure to high temperature, and we need to offer some solution. So this covers the domain of structural repair and retrofitting. Normally we have to offer solution in these type of situations. And as I said in my initial remark, that corrosion is a major factor, and I'm going to discuss corrosion bit in depth, or because 90% of projects are because of 90% of issues, structural issues are because of corrosion. We can see this beautiful structure in this particular site, and you will feel that this is a building ready for possession, and actually it is ready for possession. And then so again beautiful building, closer view of that, and suddenly we get this type of cracks. You will definitely get shocked that building as old as 2 year and 3 year is getting this type of corrosion. I put these slides just to show you severity of the problem, corrosion problem. And in this case, this is accelerated aging of the structure. Means the structure which should have been corroded after 30-35 years is showing this type of distress within 1 or 2 years. And it's really point of concern for us how to repair and tackle this type of situation. So cost of construction or cost of corrosion, we have to pay huge cost, I would say. First is the structural safety. It may lead to this type of structural collapse if your corrosion is excessive. Corrosion is a big industry. It's almost $1.3 trillion industry. The corrosion and tackling corrosion and problems created by corrosion. And then environmental also, because steel corrodes and we need to put additional steel. And definitely to produce the steel, we need to put a lot of energy on it. So it's create a lot of pollution also in the process. So cost of corrosion is huge, safety, financial and environmental. So why metal corrodes? Everybody knows that how metal is produced or how steel is produced. Basically, steel is produced from iron ore. Iron ore is nothing but a stones. If you have seen iron ore, you cannot differentiate between stone and iron ore. We put a lot of energy on that ore to extract metal or to extract the pure form of steel, and then we get this type of steel which is malleable, and we can make sheet, we can make rod out of it. So by adding a lot of energy on ore, we produce the metal. But then what happens in corrosion is exactly reverse. It's a loss of energy. The moment you make the metal out of ore, it likes to go back to its original stable state of ore by losing the energy. So corrosion in another way is nothing but loss of energy over the period of time. And what we can work on is to increase the time taken or to conserve this energy, how to avoid the loss of this energy. So in case of RCC, it's interesting because concrete is like a stone, so concrete doesn't corrode. Issue is with steel. Rather, concrete is a very good corrosion inhibitor. It got very high resistivity, it got low porosity, and it got high alkalinity, which are very conducive for metal, and there should not be any problem to metal if it is maintained. And this protective layer of alkalinity protect the steel from getting corroded. This layer protect the steel from getting corroded and conserve the energy. If you see the pH value in this particular graph, on x-axis is a pH value, on y-axis there is the rate of corrosion. And if you see, concrete is a highly alkaline material. So as long as your pH is in the range of say 10 to 14, rate of corrosion is less. The moment your pH reduces, rate of corrosion increases. So what happens there? That a protective layer that holds the energy in normally prevents the steel from corroding. This is the layer I'm talking about. But there are two disrupting factors which normally disturbs your passivating layer. Those are carbon dioxide and chloride. If you imagine concrete as a hard sponge, and it is a hard sponge, if you see the molecular size of H2O, carbon dioxide and chloride, all these got very small molecular size that can be easily penetrated through this spongy concrete. And it will be interesting to see how this carbon dioxide and chloride affects the behavior of steel inside the concrete. First of all, carbonation in concrete. Carbon dioxide is available in environment, and we have a lot of COH available in cement place. COH nothing but lime, and carbon dioxide is amply available in environment. As long as this COH lime, its pH is low in the range of 13 and 14, so it's in alkaline range. So in this range, your passivation film is intact. The moment it reacts with carbon dioxide, it forms calcium carbonate, and your pH drops up to 9, gradually and slowly, and it tries to go into this acidic zone. And the moment it pH start reducing, your passivation film get dissolved and corrosion starts. So this is a preliminary reason for corrosion in RCC. Normally, if you see the rate of reaction of carbonation, it's K into square root of T, like uh, uh, T is a time required and K is a coefficient of diffusivity of carbon dioxide. For a normal concrete, I would say that rate of, by thumb rule, means rate of carbonation is around 1 mm per year. That's how you keep this cover of 40 mm. So by the time your corrosion will reach to steel, you will have a usable life of around 40 years. So that's what minimum we expect from steel, and that's how it protects the steel from not getting corroded. But if your concrete is porous, naturally rate of carbonation will be more and you can expect early corrosion. Second factor is chlorides. Chlorides are amply available in like coastal areas like Mumbai. We are near sea and we get a lot of corrosion, or India got long coastline, and wherever there is a coast we have problem of chloride, and there is a moisture also along the coast. So this chloride can penetrate through the uh, concrete and can disturb your passivation film, and it will start corroding your steel. And this is a chloride attack on steel, and you can see reinforcement is really losing its cross-sectional area. Will have consequences on means corrosion is an interesting phenomenon. I say that if pure Fe is 1, volume of corrosion product will be 7. So steel will expand 7 times than that of its original volume. And during this expansion, there will be volumetric strain generated inside the concrete. Concrete is a strong material in compression, but it's not that strong in tension, and it cannot accommodate this type of high expansion in volume, and we can see it start exerting these tensile stresses on concrete, and concrete fall. And when it's fall, we start seeing this type of reinforcement. Again, actually I tried to keep less number of graphs, but still I could not resist putting few graphs. So in this particular graph, it is elongation versus load, and for different rate of corrosion. So this red one was a virgin steel, and you can see that as long as steel was not corroded, its stress strain behavior was perfect. It is showing this beautiful ductile behavior, so it can elongate a lot. But as it corrodes, it loses its elongation also, and its overall behavior reduces, and this will have consequences on its structural integrity also. So how it affects? Like this. Because of this corrosion, steel will reduce its ductility, and because of reduction in ductility, it will reduce its structural capacity also, like axial load, bending load, and shear load. And this will lead to brittle mode of failure, which is not desirable for any safe structure. So this becomes more important that we look corrosion not only from durability perspective but also from strength perspective. So let's come on solution. You know how steel corrodes, and once steel corrodes, you get this type of spalling. And what I found that we try to do some quick fix, and we try to do funny solution, but that doesn't really work. We try to treat symptoms, wherein we need to try and fix root causes of the corrosion. Treating symptoms will not help in addressing the problem. So if you need to decide strategy for corrosion repair, it will be like this. Can be the options we have. These are the options we have available, like patch and repair of cracks and spall, remove and replacement of contaminated concrete. Here contaminated means concrete which is carbonated and which is infested with high chloride ions. We can go for some topical treatments, and then we can have electrochemical solutions. I will describe all this in subsequent slides. So normally we come across this type of initial condition. These are the condition we see some minor surface crack on the surface of the concrete, and that's when we come to know that there is some issue with my RCC and I need to treat. Ideally, we should remove all the contaminated concrete like shown in this slide. Remove all the contaminated concrete, and then we can replace it with different, and we can rebuild the profile by using different chemically activated mortars which are available in market, polymer modified mortars, micro concretes, graniting, or whatever best suited for that particular situation. But we need to know what happens when we do patch repair. Normally when we do patch repairs, only it protects the steel within the patch, and in the process it can accelerate the corrosion around the patch, typically like this. Normally, as I said, corrosion is an electrochemical process, so there is a formation of anode where we normally see the spoiling of RCC, and at cathode zone you will not see the corrosion of steel. This particular situation, localized cathode and anode, arises because of local honeycombing or local issues with this concrete. And once we treat this steel, this anode, previously anode, become cathode, but subsequently nearby two areas become anode and corrosion start there. So this is typically called ring effect. So when we are doing patch repair, we need to careful that we don't need to, so this is a cathode after repair and this is anode. So we can introduce this type of zinc anodes so that we have a sacrificial anode here and entire steel can behave as a cathode area, and it can be put like this to the reinforcement. And we did a small experiment in our lab, like this is a one cage which is put with this sacrificial anode and one without sacrificial anode, and you can see the difference. This is corroding quite rapidly, but whereas this sacrificial anode is protecting the reinforcement. Then if we do only membrane and barrier and sealer, so you can see here this particular concrete already infested by chloride and carbon, and you are doing this only additional membrane, so it will stop the further increase of carbon dioxide and chloride, but inside elements are still present, and these will be responsible from corroding, and you can still see this type of patches in and you will find that your treatment is getting failed. Then we have a topical treatment or migratory type of corrosion inhibitor which can be applied on concrete surface. It got very high affinity towards steel, so it will pass through the concrete and it will protect the steel reinforcement inside. Those are available in this type of capsules also. It's like vapor phase inhibitor. It's like your naphthalene balls, so it gets vaporized and it will protect the steel inside. So in modern repairs, which can be like this typically, and in corrosion you can do as many as options you can take depending on the importance of structure. So in this particular case, we are putting zinc anode, then we are putting this type of caplates and MCI treatment also to protect the steel. Then we have electrochemical solutions like galvanic protection and impressed current system. We saw that corrosion is nothing but loss of energy, so we can add or put additional energy to keep the steel in its original condition, and that can be added by creating this type of galvanic potential where we can put sacrificial anode on concrete and we can connect it to steel, so this anode will sacrifice and it will protect the steel inside. It delivers a small current through the concrete to the steel, and which the previously corroding anodic areas will receive that current, and those will be converted into cathodic areas, and by the way corrosion will be arrested. Other is a more active method like impressed current method, where we can introduce this type of ribbon, and we can have a external power supply, and we can make it a permanent anode, and we can make it as a permanent cathode. But these systems are generally very expensive, so it will depend on the choice will depend on the importance of structure. And repair procedure is very important. In this particular slide you will see that if you don't do proper surface reparation and you simply patch up without proper surface reparation, after a few years you will find that these patches will removing at the ends. So what should be the, again, deciding repair geometry is also important. If you have this type of damages, ideally you make a proper cuts, and it is recommended to have a proper geometrical shape instead of having irregular shape and putting different maps of corroded of repair patches. So we prefer, or even code says that it's better to have a ideal geometric shape for that. Then we can create this type of end wedges, and ideally we should remove all the carbonated concrete around the reinforcement, clean the reinforcement, and fill it with your better performing mortars. I'll just show you one case study of this type of corrosion damage structure. You can see it's a marine structure, and these are basically transmission tower foundation traveling through creek, and this type of damages were there. So this was the procedure: surface preparation, steel treatment, concrete impregnation, structural bond coat, section reconstruction, fiber wrapping, and protective coating. So as I said, it's very important that we remove all the weak patches and clean the surfaces so that it can receive the further treatment. So again, we applied MCI and cleaned the reinforcement with alkaline rust converter to protect the alkaline environment around the steel. Then IPN coating over it, and wherever required we went with grouting, and we built the surface in this case with micro concrete. Like we put this type of formwork, and we pour the micro concrete, and we rebuilt the structure, rebuilt the profile of the section. These are the glimpses of corrosion repair. Now I will come to advanced structural repair and retrofitting. Like, new construction process is very well defined. You know your function and structural demand, and before actual starting construction we spend a lot of time on architectural part of it, its engineering, its economic, its construction method. So before we start construction, a lot of time has been devoted on all these aspects. So it's pretty biased on this planning side before actual construction. But when it's come to repair retrofit, we have a different challenges. First is like we have some structure having some existing capacity, and then we have some new demand because of earthquake or because of additional load, and we need to achieve this by following some strengthening measure. But normally we find that becomes the strengthening process is not that easy, it's pretty complicated. So what happens that in case of retrofitting, your constructability, aesthetic, and time taken for repair and cost is a major factor, and that will decide your engineering. Means you have to spend a lot of time on existing site because your structure is already there. You need to understand the stress level, what are the limitation, what will be the shutdown time you will be getting, and accordingly you have to do engineering. So it is typically nothing but a reverse engineering process. So I always say that repair retrofitting is nothing but reverse engineering process. So it should start from site to office rather than from office to site. We have different strengthening techniques, like conventional strengthening technique like steel plate bonding, external bonded FRP, concrete section enlargement, and external post tensioning. And we can use hybrid solution which are comprising of all this thing. We'll just look at the features, benefit, limitation of all this method in subsequent slide. If you ask me what are the proportion of different strengthening scheme which are currently in vogue, so almost in our case, at least 50% solutions are based on FRP and rest of the systems are 50%. We can follow two approaches when it comes to retrofitting. First is to increase the capacity of the system by FRP wrapping or concrete jacketing or steel plate bonding. Or we can reduce the demand on the structure by putting dampers, then base isolators, and TLD, like tune liquid dampers. Normally 95% solution are based on this strength approach, wherein we actually increase the capacity of section, and we can do a lot on this section, but a lot of the discussion will happen on this particular part, like increasing the capacity of the structure. These are the conventional measures where you can increase the size of the section by putting some additional concrete or RCC. We can do external post tensioning for this type of shear cracks. And then we can use composite. Composite is, though we are using composite in India for last 15-16 years in construction, but composite is a very popular material for defense industry because the lightweight, strong, and being non-metallic material, radar cannot detect it. So that's why it become very popular in defense industry. And at the end of Cold War, these material are freely available for maybe civil engineer for repair and retrofits. So like RCC is a composite where steel in the reinforcement, concrete is a matrix, and which gives the shape. Similarly, this composite comprises of fiber phase, filler phase, and matrix phase. In fiber, we got different type of fiber like glass, aramide, Kevlar, and in matrix mainly thermoset or thermoplast resins. If you see the mechanical behavior, it's a bit different than steel. Steel is the elastoplastic material. Once it yields, goes into this plastic phase. Unlike that, composites are elastic, means its yield point and failure point is same. It's a straight line relation, so it doesn't have this beautiful plateau. But its ultimate stresses are very high compared to steel. And again, one property is its orthotropy. Like whenever we design steel or RCC, we consider the isotropic homogeneous, means properties are, all mechanical properties are same in all XYZ direction. But that is not a case with composite. It is an orthotropic material. So you can see this fiber are oriented in this particular direction. So it is very strong in one direction. We call it unidirectional. So very strong in this direction and weak in the other direction. So this is a very important property, and one has to be very careful at the time of application where we are orienting these fibers. These are available in different forms, like this type of wraps, which can be wrapped around with resin on RCC element, or this type of procured carbon laminates of different thickness and widths, which can be applied on soffit of the concrete. So for column, we can apply for flexure loading like this, vertical wraps, and then for shear, horizontal wrap, or both the wraps depending on the requirement. For beam, we can go for flexural wrap, again for shear wrap, and if required, both flexure and shear. For one-way slab, we can wrap in one-way direction. For negative moment, we can wrap it from top. And for two-way slab, we can wrap in both the direction to take care of bending in both the direction. What are the advantages of FRP? First is no corrosion. It's non-metallic system, so not going to corrode. So very good where exposure is severe, marine exposure or chemical exposure. It's higher ultimate strength. It's higher reactive modulus. Very good fatigue properties. Low weight, density of this material, you can say it's very light material, this type of rod, or as I said, these are the wraps which can be wrapped around. So it's a very lightweight and non-metallic type of system, and it can be bent in any direction, so it can be wrapped around the section very easily. So it is a very less time consuming process compared to conventional system. Then its behavior, again on x-axis there is axial strain, on y-axis there is axial stress. This is a bare concrete. I am wrapping with single layer of this glass fiber, and you can see bare concrete strength was around M25, and with single wrap its strength is going to around M70. As I am increasing number of wraps, my strength is going up. Not only that, you can see area under this curve, black curve, and area under this yellow curve. This area under this yellow curve is much more than area under this black curve, indicating high energy dissipation capacity. And that's what we look for ductile detailing, or in case of earthquake, that structure should able to absorb a lot of energy. So wrapping is really helpful in that case. It can absorb a lot of energy. Similarly for beam, RCC beam, this is deflection versus force, and you can see this is an existing RCC beam, and I want to increase this flexural behavior, and I can put this type of carbon laminate, and you can see its flexural strength is going up considerably. Then there is always a question asked that how to design FRP system. So there are different codes available and guidelines are available, and we can follow any one of this to design, repair and retrofit system. Here I'll come at the different case studies that we have dealt with. In this particular case is a consulate building. It is one of the early RCC construction in Mumbai, 1942 construction, and client wanted to put strong room over this, and column were weak, concrete were weak, and not capable of taking that additional load of strong room. So it is decided to strengthen this column by putting additional wrap. Then this is for a podium slab. In this particular case, there was change in use. Client got additional FSI, so he put some additional 4 on top, and he converted this first floor into a podium parking. Naturally, this podium parking was not designed for vehicular load, but it was designed only for your normal live load. So it was a two-way slab, so we wrapped in both the way, X and Y. Beams were naturally failing in shear, so we strengthened the beam in shear zone and as well as in flexural zone. Then very first case study in India of this application was at IFCO Kandla after Bhuj earthquake in 2001, and this was these were the different damages, typical shear failure. You can see it here that there are no shear lengths, so naturally you can see failure at this particular spot. This is soft story failure where column is completely getting shear off at soft story, and in this particular case, being a fertilizer plant, it was exposed to phosphoric acid. This was near the coastline, and this plant was insured for earthquake damages. So whatever money client will spend on earthquake retrofitting was covered under earthquake, but loss of production was not covered under insurance. So client wanted to start plant as early as possible, so that's when we gave this solution based on FRP. So all these joints were restored by following conventional repair method, and then joints were wrapped. It's almost now 17 years, and still you find that being non-metallic structure, even though it is exposed to very aggressive environment, still these elements are performing in a phenomenal way. Then there is a case study of this cold storage structure. You can see this type of damages. Again, here you can see steel is buckled. So what was the reason? This is a typically RCC cold storage structure located in New Bombay. All the intermediate floors were designed for higher loads like 1500 kg. But terrace was not designed for higher load. Terrace was designed only for 400 kg per square meter load. During monsoon, what client did, he kept he stored all the leftover material on terrace and covered it with tarpaulin. But in the process, he loaded it too high. Means he loaded almost 1000 kg per square meter, and terrace was designed only for 400 kg. And naturally, there were corrosion also. Bar also lost its capacity. So this failure happened. So what was the solution? That structure was immediately supported by putting additional prop, then additional load was removed, additional steel bars were provided, then grouting was done using low viscosity epoxies, corroded steel was treated with protective coating, and sections were jacketed with micro concrete, and it was wrapped with almost 3 layers. And beauty is that entire job was completed in 15 days so that he can start using its cold storage again, so that minimizing his business losses. Then this is for a chimney somewhere in south. You can see this chimney, and its height was around 60 meters, and outer dia was 3 meter. You cannot make out with naked eyes, but chimney was swayed almost by 273 mm while casting, and this eccentricity put the structural stability in doubt, and client was really worried that how this eccentricity will play its role, because structure is designed as a concentric structure, and because of this induced eccentricity, how will it impact the stability of structure. So first we found out the eccentricity in all these 4 quadrants of the structure by total survey station. We need to know exactly eccentricity in all the direction to model the structural eccentricity properly, and using that eccentricity we remodel the structure with finite element based models, and we found out what is the additional stresses at the base because of this eccentricity. And then we came up with solution for this, like we introduced this additional laminate at the base where maximum tension was there up to 12 meter. Then we did a helical wrapping for the entire chimney to take care of shear and bending at the top, and base was wrapped up to 12 meter. We wrapped the base entirely. So these are the photographs. This is a chimney, and as you say, the bottom is put with carbon laminate, and then followed by wrapping, and above helical wrapping was done. Then there is again an interesting case study of a silo structure, RCC silo structure. This was a silo structure, and immediately after putting it for its use, it was a coal storage silo, and immediately after putting the coal, we could see this type of cracking. At closer look, you can see this, wherein you can see that concrete is completely disintegrated, and bars are buckled like this. And if you see from inside, there is a through and through cracking, and cracking is at the most critical location, means just below the your ring beam of a hopper. This is a hopper, and just adjacent to this there is a through and through cracking. It was a multi-cell silo. 4 cell were constructed at a time. So typical geometry was like this: 4 cell constructed at a time. So geometrically, it was a very good geometry in terms of its stiffness. All 4 tubes bundled together. So it shouldn't have been collapsed if it has casted properly. So what are the preliminary reasons for failure? First is a handling issue with multi-cell slip form work. This entire silo was casted using multi-cell formwork technology, and they used to start casting from this point, then fill it, and then come to this and fill it. In the process, they could not control the initial setting time of the concrete, and whenever slip form were pushed up, it left the weak pockets of the concrete, and those created a weak zone in silo, and that created the problem. So bad quality of concrete, inadequate curing, and very optimized design. Design was optimized because they were taking the advantage of this geometry, and that's why shell thickness were less. So very optimized design. So immediately after this this failure, it was important to support the silo, because everybody was worried how to support the silo. Fortunately, this type of stanchions were available in that particular factory, so we could immediately support the silo by putting this type of stanchion around the silo to take care of its buckling. So this was the geometry. This is your hopper. This is a hopper. These are the silo walls, and this entire silo was resting on friction pile. It was in eastern part of India, so it was resting on friction pile, and pile cap was there. So how to retrofit it? So because entire bar were buckled, we cannot rely on the existing steel. So we introduced steel frame internally like this. So this entire hopper load was relieved by using this type of steel frame. So this steel frame really helped in relieving the load of the hopper. Then externally, again, it was jacketed with RCC, and at top we did fiber wrapping. It's like this. Up to this we did RCC jacketing, and at top we did fiber wrapping. Now you'll ask me that why I didn't continue this jacketing till top, why I opted for jacketing here and wrapping here. For the very reason that there were friction pile, and there was a limiting load. I cannot increase the dead load because my pile capacity were not that much. So to optimize the load where stress were less, we use FRP, and at the important location we use RCC jacketing. So we can optimize the load also, and we could protect the existing capacity of friction piles also. So this is the picture of a finished silo. So to project summary, like we followed the hybrid approach. In this case, I said hybrid because we did all three types of strengthening. We use structural steel, we use RCC, and we use FRP. So that's why I put this case study also, that we have to really choose our method of retrofitting depending on the problem or in hand, or depending on the restraint which we have. So as I said, all three methods were used for retrofitting, and entire work was completed in 90 days. Structure is brought back to its service successfully. To summarize the entire presentation, like what we saw, like we saw the corrosion process in RCC, and it is really an electrochemical process, and it involves release of energy. Corrosion control techniques include prevention and mitigation, and we discuss different solutions depending on the situation. Cathodic protection CP is viable technology to mitigate corrosion of steel and reinforcement. So I will not say that we discuss in details, but we just showed you the highlights, that how it can be worked and how it can be put into use. Then we saw that repair and retrofit is nothing but a process of reverse engineering, and importance of starting the retrofit process from site rather than just sitting into your office. Then selection of retrofit systems are very important, and it will be governed by site condition, time, and cost in hand, and importance of structure. So these parameters will decide which retrofit system we are using, and accordingly we can choose different retrofitting system which we discussed. Then different international design guidelines and CPWD handbook is available for design of repair and retrofit scheme. I will strongly advise you to refer this type of guidelines, and CPWD handbook is also a beautiful document which you can refer for retrofitting. These are the few of the references for your additional interest. You can refer through this to understand more of a composite. And thank you all for being with me, and thanks my team Sanrachana, which helped me in putting this presentation together, and which work on the site and committed for yeah. And now you can ask your, or you can send your question, and I'll be happy to address it. Thanks. I got this question from Goa, Mr. Olavo. What about load increase on footing? How do you check the footing capacity, and how to increase the foundation capacity? It's a really good question. We can actually do the retrofitting once we ensure that your foundations are safe. My observation is that in the project which I dealt, in 90% of cases foundations was not having issue, and that's why we could do this type of retrofitting. But yes, if there is an issue with foundation, we have to do retrofitting of foundations also. As I mentioned, CPWD handbook give different option for retrofitting of foundation, which you can refer. I'm not able to answer all these option in this brief period. You can refer that. Thanks a lot. I have been asked that which software you use for repair and retrofit. So as I mentioned, for analysis, you can use your regular software like STAD, ANSYS, and NISA. And for designing, you can design based on combination of IS 456 and ACI 440. Then is again a good question, how to balance trend during the retrofitting. Retrofitting first, before doing any intervention into structure, it is highly recommended to support it. We need to calculate what is the vertical load coming and how much load we need to augment, and accordingly we need to first design support system and then only start intervening with the structure. Then it's been asked that can we use FRP for wooden structure? Yes, FRP can be effectively used for wooden structure also. In fact, we did couple of structures using FRP for wood. Those were the termite infected timber structure. First, we need to ensure that we remove all the termite, and then we can very effectively use FRP for strengthening wooden or timber structures also. Again, I was asked about fire protection of the FRP. Yes, uh, in terms of FRP, it's important that we protect it by additional fire protection system, depending on the its importance. Uh, Normally, if you are coating it with inorganic plaster of say uh, 20 up to 25 and then followed by gypsum, you can get around 1 hour of fire rating. But if you have a specific requirement of fire rating around 2 hours or so, it has to be designed specifically. But normally it's advisable to use as a secondary reinforcement, and failure pattern needs to be established before actually use of FRP there. Again question is asked that can we use it for masonry structure, brick masonry structure? In fact, it is FRP can do a wonder in case of masonry structure, especially in fact in India 80% structure are brick masonry structure. We typically call it non-engineered structure, and those are most vulnerable in case of earthquake. So you can use FRP bands around your lintel, around your opening, and that can really give you good stability for lateral loading, and you can really reduce the casualties in case of earthquake if you use this type of FRP band for corners and lintels of the beam. And that's how it can be very effectively used for masonry structure also. What should be the quality of concrete for use of FRP? I would say that if we are using it for strengthening purpose, concrete grade should be M20, or a tensile strength of concrete should be at least 2 MPa, because that will ensure the effective effective transfer of stresses from FRP to RC structure. Then lifespan of the FRP. Again, a good question. FRP being a non-metallic is that way corrosion free, and if it is protected properly, it is can be as long as your life expected of your structure. So it can really last for 25-30 years. There should not be any problem. A lot of questions are pouring actually. I'm just struggling to select one which to answer. What care is important in choosing the adhesive? It means epoxy adhesives are good, and you should ensure that it is properly protected. If it is exposed to direct sunlight, it is advisable to protect it with PU coating, so that there will not be any UV degradation of epoxy. So you can use that. Then cost is been asked. So cost for retrofitting is really very funny. Means you can get a huge cost range depending on extent of retrofitting required. Means in my case, we have done retrofitting with as low as 50 rupees per square foot, and as 4,000 rupees a square foot. So it really depends on what is the importance of structure. For deflection, you have different methods actually. You can increase, you can put additional steel section there, and for cracking you can use FRP. So uh, that is that are the approach you can choose. Is there any NDT available for FRP? Unfortunately, no NDT available for FRP. If you want to test the performance of the system, you can wrap the cylinder or concrete with given wrap, or you can put additional laminate on beam, and you can do testing for that. But there is no NDT available for testing of FRP. uh, how to replace corroded steel? Normally, we don't need to replace the corroded steel. We need to passivate corroded steel by cleaning the scales and creating alkaline environment around that. So it can be there, because problem culprit is concrete. That environment is creating problems. So you need to protect the environment around the steel, so that we can reduce the rate of corrosion. What is the time duration for FRP? Normally, FRP is the fastest method of strengthening. So I I will say that compared to conventional method, time duration will be almost 1/4. We can really save it. We can really save the time. So whenever you are having like less shutdown time, you can go for this. So thanks a lot. There are question pouring, but we have a limitation of time, so we cannot take it all. Thanks for spending your Friday evening with me, and thanks organizer and Tata Tiscon for giving me opportunity.